Okay, in this video, we're going to talk about de Moivre's formula. This is a formula that relates, if you were to take a complex number z, if you were to write this in polar form, so this is going to be r times cosine theta plus I sine theta. And then it turns out that there's a nice formula for the powers of z. And we'll talk about this. There's a really nice underlying result here, which we'll talk about in a few more videos down the road. But for now, we have de Moivre's formula. And so this says that then if you were to look at positive integer powers of z, what you would get would be r to the n, which makes sense, times cosine of n theta plus I sine of n theta. And I think the best way to make sense of this formula is geometrically. So if you were to take a complex number z, and this has some argument, the line segment connecting the origin to the complex number z has a certain length, so that we say that the complex number z has modulus r. And if you were to multiply two complex numbers, say compute z squared, what happens? Well, you square the moduli, so you get r squared, and then you add the angles, you add the arguments together. So you would end up with z squared would be r squared times cosine of 2 theta plus I sine of 2 theta, because you're adding theta plus theta, right? And so if you were to do z cubed, what would happen? Well, you'd have r cubed times cosine of 3 theta plus I sine of 3 theta, because you would take z squared times z. Z squared has a certain modulus and a certain argument, and then you would add, based on what we know from multiplying complex numbers, when you multiply two complex numbers, you add the arguments and you multiply the moduli. So if you were to add another theta here, you'll get 3 theta, multiply another r, you get r cubed, and so on. And so you would do this just indefinitely. This holds for all. So this is true for all integers and greater than or equal to 1. Okay. In fact, let me write integers. There's another way to think about this formula, which we'll talk about soon, that'll kind of subsume this discussion here. But for now, this is a nice thing to have. And this is called de Moivre's formula. And formally, if you wanted to prove this, you could prove this by induction. So if you wanted to go through and do that formally, if you've taken a class on proofs, this is a good exercise. Basically, all you need is you would need mathematical induction, and then you would need, what is it, the sum of angles formula for sine and cosine. And I think it follows easily from there in general. Okay, so this is called de Moivre's formula. What this lets you do is, let's see, let's do an example here. Let's let W be a complex number. Okay, so let's let W be a complex number. Say W is, let's write it in polar form, r cosine theta plus I sine theta. If you want to talk about finding the nth roots of W, so let's say we want to solve z to the n equals W for z, where n is whatever particular positive integer. So we've already talked about how to do this for squares, z squared equals W and so on. But if we wanted to solve z to the n equals W for z, what we could do is we could write z in polar form. This is actually now a much easier discussion in polar form versus algebraically. So algebraically, even solving z squared equals W was a little tricky. We had to do some algebra tricks. But if we know polar form, then this actually becomes much easier. So let's write z as rho times, let's use a different value. Let's say phi, cosine of phi plus I sine of phi. Or say phi, if you want to say phi, I say phi. What I want to do then is I want to solve z to the n equals W. So we know by de Moivre's formula that z to the n is nothing more than rho to the n times cosine of n phi plus I sine of n phi. Right? That's precisely what, just to zoom out here, that is precisely what de Moivre's formula says. If you want to compute, take a number in polar form, if you want to compute powers of it, this is how you do it. Okay, so z to the n is equal to rho to the n times cosine of n phi plus I sine of n phi. Now what we're going to do is we want to solve this by setting it equal to we're going to set this equal to omega. So now remember our goal is that we want to solve z to the n equals omega. Or let's see, that means that rho to the n times cosine of n phi plus I sine of n phi is equal to r times cosine theta plus I sine theta. And what that means is that you can think about this geometrically. If you have two complex numbers written in polar form, they must have the same parameters. They must have the same modulus and the same arguments. Otherwise, you would have a different point. Okay, and that's specifically because we're ruling out the like walking backwards thing, the negative moduli. So since the modulus is positive, that's going to describe the distance of that line segment from your complex number to the origin, and that's going to uniquely determine that complex number. So what that means then is that you're going to have rho to the n equals r, and the other parts are going to be equal as well. So when you set these two complex numbers to be equal, that means that the real parts have to be equal and the imaginary parts have to be equal. And so that tells you that cosine of n phi is equal to cosine of theta, and sine of n phi is equal to sine of theta. And what that tells you is that these actually must be the same. This is n phi plus, that has to be equal to theta plus some multiple of 2 pi. And same here. This is theta plus some integer multiple of 2 pi for some integer k. Okay, and so it turns out that the values of k where this will be meaningful is the values of k going from 0 to n minus 1. Okay, and so really what this means is that you can solve for rho is super easy to solve for. Just take an nth root, and because everything's positive. So this tells you that rho is equal to the nth root of r, and phi is equal to theta over n plus 2 pi k over n for some integer k. Okay, so it turns out that you get distinct values. What I mean is that the values of k should get, or the values where you get distinct values, you get distinct values where k is between 0 and n minus 1. I'll let you think about what happens when k is equal to n. Okay, so I'll let you think about that. Or 2n or whatever you want. So the distinct values that you get for k are where k is between 0 and n minus 1. And so what this tells you is, this tells you actually now a formula for taking nth roots. So if you were to solve z to the n equals w, where w is r cosine theta plus I sine theta, then your solutions are going to be all the complex numbers z, which are going to be in polar form, rho, which is the nth root of r, times cosine of phi, which we said is theta over n plus 2 pi k over n, plus I sine of theta over n plus 2 pi k over n. And again, I'm out of room. Where k is allowed to range between 0 and n minus 1. Okay, that's the values where you get distinct terms. Okay, the reason why these are the values where you get distinct terms is that as soon as k is outside that range, then you're already repeating a term, right? If k is equal to n, then this is just going to be 2 pi, and then you get the same value as when k was 0. So you just get a repeat term, and likewise for all the other values of k. So this is a nice formula for finding the nth roots. And this tells us a few things again about finding the roots of unity. So let's solve again. Z to the 8 equals 1. Let's find the 8th roots of unity, but now using this formula, which comes from de Moivre's formula. And so Z to the 8 equals 1. What we're going to do is our 1 is our W. So 1, we're going to think of as the complex number 1 plus 0i. And The modulus of 1, it's hard to write it, so let me write 1 like that. The modulus of 1 is 1. The argument of 1 is 0, because you always start at the rightmost point. That's the convention, and I'm backwards on the screen, but you always start at the rightmost point. Let me draw it. It's just like in trigonometry, and you get this basically from parameterizing the unit circle, but you always start at the rightmost point, and then you're going to travel counterclockwise. So if you're thinking about this number here, 1, well, it's going to be distance 1 from the origin, and the angle that it's going to make with the x-axis is theta equals 0, so 0 radians. So that's our theta is 0, and our r is 1. And so that tells you that your nth roots of unity are going to have a nice formula. So let's do this first for the eighth roots of unity. So it tells you that you're going to have z is going to be the eighth root of 1, which is 1, times cosine of theta over n. Theta was 0, so we can get rid of that. 2 pi k over n plus I sine of 2 pi k over n, where k goes between 0 and 7. Again, as soon as k gets to 8, then you're repeating yourself by traveling along that unit circle. You've traveled 2 pi radians, so you're starting to repeat yourself in double values. So this tells you that you're going to have 8 different solutions, and it's going to be these solutions. So in other words, so let me write this one more time. The eighth roots of unity, z to the 8 equals 1, are going to be the values where z is cosine of 2 pi k over 8 plus I sine of 2 pi k over 8. And in fact, let's just algebraically simplify that to cosine of pi k over 4 plus I sine of pi k over 4, where k is between 0 and 7. And so when k is equal to 0, you end up with 1. When k is equal to, so this is k equals 0, you get k equals 1, k equals 2, k equals 3, 4, 5, 6, and 7. And then when you get to k equals 8, you get back to 1 again. So that's why we only go from 0 to 7. So that's another way to think about the nth roots of unity. So what this tells you is that in general, the nth roots of unity, so z to the n equals 1, the solutions to that equation are called the nth roots of unity, are n equally spaced points on the unit circle, starting at the rightmost point 1. So 1, or whether you want to think about it as a complex number, 1 plus 0i. Okay, so that's the nth roots of unity. So if you wanted to talk about the fifth roots of unity, that would be that point somewhere over here, somewhere there, there, and there. And those would be your fifth roots of unity. Okay, and so on and so forth. Okay, so that's the nth roots of unity, and how de Maurer's formula helps us with that.